Hello, hello. Today I want to go over some some physics and some calculus. So I'm going to focus on this particular formula. It's just of interest to me, but you could really do this with a lot of different formulas. I mean, probably with any formula, just not necessarily the exact same setup. So we're going to use force equals K times, I'll just write it as absolute value of Q1 times absolute value of Q2 over top of R squared. Okay, and so so this is the basic formula. And what this formula means is, say we're trying to find the electric force between two charges. I'm gonna blow this down a little. So let's say we have some charge here, it's positive, some charge here is positive. So we know just the general physics principle, which if you didn't know this, you could perform some tests with charges and see it, but the charges always repel one another. So like charges always repel one another. So they're going to experience equal and opposite forces away from one another. So let's say if this were Q1, this were Q2, this would be force of 1 on 2, and this would be force of 2 on 1. And to go with the rest of this here, K is a constant. It's always 8.99 times 10 to the ninth newtons times meters squared over Coulomb squared. And yeah, that's what K is. R is the distance between the centers of these charges. So from the center of Q1 to the center of Q2, that's R. So what this is saying is, say we have this setup. If we want to find the force that either one of these is acting on the other because they're equal and opposite. So this just gives the magnitude of the force. The direction is determined from the physical setup. But we would just plug in K, Q1, the charge of Q1 in coulombs, the charge of Q2 in coulombs, and the radius in meters, square that radius, like what's written here. And you would get the force in newtons. And obviously you can manipulate this any way you want. So if you wanted to find the radius, it would be, I said radius, it's the distance. So radius, distance equals the square root of K magnitude of Q1 magnitude of Q2 over F. So that would be, if you had all these values but you didn't know the distance between the two charges, you could use this formula, and you can solve for anything you want. So if you wanted Q1 equals the force times the distance squared over top of K magnitude of Q2. So let's say that technically this is also magnitude. So let's say the magnitude of Q1 is unknown, and you know these other values, you can plug them in like this, and you can get Q1, and so on. But let's say we want to calculate the electric force between charges, but we have some different setups than what we have right here. Before I get into that, there's a couple things I guess I want to go over mathematically. So I wrote this way. There's other ways to write this. We could write it as force equals K Q1 Q2 over R squared. If you wanted, you could write R between 1 and 2. You could always write that or always leave that off because that's what the displacement is between 1 and 2. And so if you have this without the absolute value signs, what it means is it's still going to be exactly the same, except what you'll notice is if you have two positive charges, then force will be positive because R squared has to be positive. K is always positive. So a positive Q times a positive Q will make a positive force. But also if you have two negative forces, then you would have a negative Q1 times a negative Q2, and force will still be positive. Negative here, and we have a force acting this way. Now, what if Q1 is negative and Q2 is positive? Well, we're going to get a negative answer for the force. But it's not so much that the force is negative. It may or may not be. It depends on how you set up your how you think about it conceptually and how you set up your axes. Here, the negative sign happens to mean that they're pointing inward, which you can see here. Opposite charges attract, and the same will be true if Q1 was positive and Q2 was negative. You'll see that the charges attract toward one another, and a positive times a negative would give you a negative force value. So if you read it without the absolute value signs, you can do that, but you just have to know what the positive and negative sign means. It's not quite what we would normally think of a positive and negative sign as meaning. And the other possibility is, well, there's many other possibilities, but another one that I want to go over is, so force is a vector. I drew it as vectors over here, but these formulas as I gave them are really just finding the magnitude of the force. So we can also write it as a vector, which this is going to be necessary for some problems we're going to go over. So if we write it as a vector, force equals K, Q1, Q2. I think this should be the magnitude of Q1 and Q2, but I'm just not going to write it. R squared, R hat. So you notice that this is the magnitude, because it was the magnitude in these other ones, times R hat. R hat is just the unit vector direction. So if we take the magnitude and multiply it by our appropriate direction that R is in, that will give us the direction of the force. And I suppose you could keep the signs, but it's going to matter. One of them will end up correct and one of them will be incorrect. So like, based on the way I drew these, if I put the x-axis at Q2, then positive would be to the right, negative would be to the left. So these two give negative results and they point to the left. These two give positive results and they point to the right. But if I put the axis at Q1, these, or not, it's not so much Q1 and 2, because I can flip, this could be Q2, this could be Q1, but the point is that if I put the axis on the left hand, the charge that is on the leftmost, and then I want to think of negative x direction as left and positive x direction as to the right, then these will actually be the reverse. So you'll see that this was a positive answer, but the vector points to the left. This was a positive answer, the vector points to the left. Negative answer, vector points to the right. Negative answer, vector points to the right. So the negative sign, you can still keep it. It'll be the same here. All that this is basically going to do is tell you the angle of rotation. So if we have, I happen to draw these all like on the x-axis, but let's say they're not. So let's say we have this charge, positive charge, and this positive charge up here. This is R, and R is a vector. And R is equal to the magnitude of the vector times the direction of the vector, which is R hat. So that's what's going on over here. And yeah, that's pretty much it. We're gonna need this later. So I guess the other thing, I'm probably not gonna go over right now, but another thing that's useful is you could say, let's see, will this work for this example? All right, let's say you have, yeah, we could do this, but I don't think it's gonna be easy to set up. I'll try it anyway. So let's take another example here. I'll leave that one up there for reference. And we don't need this one right now. So, let's see who messaged me real quick. All right, so if we take, where'd my mouse go? Let's say that we have this charge Q1. Let's draw it on the other side. let's put it over here. Let's say this is Q1. Make it positive. And let's say we have these other charges. Positive, negative, positive, and I'll start to use other colors now. So we'll use red, yellow, and blue. So let's say this is Q1. That would make this R1. That would make this the force of, well, I made them both Q1. So let's make that original one Q0. So this is the force of 1 on 0. And let's use yellow. All right, so if this is Q2, then this is R2, and this is the force of 2 on 0. And let's say now green, we're going to take, this is Q3, this is R3, and this is the force of 3 on 0. So now we have 3 forces, and to find the net force, we would have to combine all of these 3 forces. And when you add vectors, the easiest way to do it, and what's going to be relevant for right now, is you break down the vector into its component parts. So if we imagine the x and the y direction, the way that you would probably naturally visualize it in this situation, then we see that the force of 3 on 0 points at approximately a 45-degree angle. The force of 1 on 0 points in approximately a negative 45-degree angle. Those may or may not be 45, it just kind of looks like it in the picture. I didn't give these angles values. And the force of 2 on 0 looks like it is approximately aligned with the positive x direction. So to find these, let's get back to purple again. Actually, I'm going to use 2 other colors that I haven't used. So how about orange and, what haven't I used? How about gray and brown? All right, so we use brown for horizontal. So the force of 3 on 0, let me get back to purple for a second. If we assume that this angle is theta, that would make this angle theta. And for the sake of argument right now, let's just assume this is also theta. And let's say that Q1, 2, and 3 all have the same magnitude. Let's just say all the Q's all have the same magnitude. And oh, I drew this force in the wrong direction. Whoops. Well, whatever. We'll just make this a positive charge. It's going to be easier than redrawing the picture. So let's say this was a positive charge. I accidentally drew the force in the wrong direction there. Positive, positive, positive. So let's say they're all protons. And all right, so now what happens is the net force is going to equal the vector sum of these forces. So in the y direction, the f of 2 on 0, let's assume that's parallel with the x-axis. In that case, the y component of the total of the force vector is 0. So what's the y component of f of the force of 3, charge 3 on charge 0? Looks like this. And then the force of charge 1 on 0, I like the dotted better, looks like this. And because because these angles are the same and the charge values are the same, these have to be the same length, the same magnitude, and the vector sum of these is actually also going to be 0 in this case. Now if, let's take maybe pink. Now in the x direction, you could draw it here and do like I did, draw it straight out and then do dotted lines up, or that will have the same length as this. It's going to look a little less messy if I draw it over here. So this is F30x. So it's the force of 3 on 0, the x component, or the x component of the force of 3 on 0. This one is the, well, it's hard to say it and write it at the same time because you don't write it and say it in the same order. So this is the x component of the force of 1 on 0. And this doesn't change at all, actually. This is still the force of 2 on 0 since it was all in the x direction. So the vector sum would be to stack all these up and add them together. So if I eyeball it here, it's going to be approximately this length plus this one here, which maybe that looks like that, plus this one here, maybe that looks like that. So this length is the total length. This is the net force in the x direction. So there's some vector math. And now to kind of put that all together, now the way that I would write that mathematically is I would say the force equals, in this case, K1, I have the same, so it should be K, not K, Q1, I mean Q0. Q0 times, I think, hold on a second, let me get a little more room because I think this is going to be the magnitude of the force. K Q1 times the sum I of Q I over R sub I squared times probably R sub I hat. I think that's how you write that out. So to expand that a little bit, it would be, so this is the net force. And to write that the same way, but with our specific example, would be, because this is for any number of charges, like if this is supposed to be a 0 here, Q0, as long as Q0 is one charge and then however many other charges, this represents all the other charges. But to expand that out, we could say the net force. The reason I was thinking, I could say the magnitude and then leave off this r hat, because I'm not sure if this is proper notation to say r hat sub I, but it seems like it should be, so I'm going to leave it. The net force equals K times Q0, and in this case, to sum those up, we're going to have Q1 over R1 squared plus Q2 over R2 squared. And technically, I think I need to put, so this would be R hat 1, R hat. So this should be 1 to 0 actually, 2 to 0. Maybe this should be like I to 0. Not really sure if this notation's proper, but we're going to live with it. Plus Q3 over R3 squared R3 0 R hat. I think actually what you would normally do is just write the zeros down here, R1 0, but I'm not sure off the top of my head, so we'll do it like this. There. So mathematically this is the same as what we did up here. So there's how you do it if you have more than one charges. Now let's get into some really fun situations where we basically, so a more mathy way to say it is we're going to use calculus to solve the problems. But what I prefer to say at this moment is that we're going to develop new formulas. We're going to, because, so this up here on the top left, oops, this is a formula. And somehow somebody come up with this formula, they discovered this formula, they recorded it down. So now we know whenever we have a setup that matches the proper setup for the formula, we can plug in the numbers and just do algebraically solve it and come up with our solution. Okay, so we prefer finished formulas in a form that only requires algebra to solve. So what we're gonna do is we're gonna apply this formula to some different situations that the formula technically can't apply to directly, but we're going to take calculus and extend this formula to generate new formulas. And that's how I want to think about it right now conceptually. So, let's do. So I actually have some examples here because these are kind of hard, so it's quite possible I'll make some mistakes as I'm trying to do these. But let's say that we have this. It's like a wire, or maybe like a thin plate bent in a circle. But this is a semicircle, okay? And this is some charge right here. And I'll probably just deal with all positive charges for right now. It wouldn't really matter, because positive and negative, it's just going to change the direction. But because I have to choose one, I'm going to choose positive. So this is a semicircle, and this sits dead center of what would be the whole circle. And this bent wire, or whatever exactly it is, has a uniform charge density. That's going to be important too, or that may be important, depending on how I choose to solve this. It can be important. So, okay, so let's take our basic formula. Force equals, I'm just going to leave the absolute value signs off. Q1, Q2, yeah, I'm not going to need them right now anyway because I chose all positive. R squared. Okay, so this is our basic formula. The issue is, let's say this is Q1, which we'll just call Q, little q, and this is Q2, which we'll call big Q. Big Q represents the whole, I don't want to write that there, represents this whole object. That's what big Q represents, the charge of this whole object. So the issue is, what's the direction from this whole object to this little point charge? There is not really a one direction, right? You have force pointing from every place. Well, these aren't the force vector arrows. This should actually be this would be the R. And on the opposite side, then you have all of the forces. So this one goes through. So there's a force like this. There's a force like this. Force like this. Force like this. And like that, except it actually covers this whole thing completely, 100%. So you just completely color that in. So that's what's actually going on. So then we might ask ourselves, well, what can we do then? How can we find the net force on this charge when it's just going to be this colored in mess? And actually what it would look like is, if you were to sit there and draw every single line, you would end up with this shape, which basically is going to be like the inside of the circle. Just imagine that. Well, I think if I do this, there. So that would be the what your actual would look like. But then how do you sum this? How do you figure out, well, what value does this represent? That's what we're going to go over. And actually, now that I look at this, I think you could do it a completely different way that's graphically, but I'm not going to do it that way because that's not the way that I set out to do it. Let's try to get these colors all back how I want them. Get rid of this ugly mess. All right. So we have this once again. And now we're just going to pick one place on here, right? So let's just pick this little sliver right here. But imagine that it's an infinitesimally small sliver. Infinitesimally skinny in this case, because this can be thought of as a wire. The thickness is not going to matter. So think of it as a wire. and we'll call this dq. The d is calculus notation for infinitesimal. So this is an infinitesimal piece of the charge, except actually, since I use little q and big Q, this is actually dq, big Q. It's an infinitesimal piece of the large charge here. Now we have this is our distance. This distance represents dr. It is the r value associated with our infinitesimal piece of this charge wire. Then we have this coming on the other side is our force vector. This is df. This is a vector. This is a vector too. I guess I could write it there. So, well, technically, they usually leave it off actually, because that's why you put the r hat at the end. So I'll leave it off. Right. So, yeah. So this is what one infinitesimal piece of our final net force looks like from the one infinitesimal piece of charge. Now, what we want to do is, so instead of solving for f, we're going to solve for df. So df equals k times little q, which is this one, times dq, which is this one, over top of r squared. Yes, times r hat. Because here we don't want just the magnitude, because when we sum them all, we're not going to be able to just sum the magnitude because they don't all point in the same direction as I showed earlier. They point in different directions, so we're going to need to take the direction into account when we combine them. So this is what we have here. And now we have a formula, although this one's not really that useful yet, but this is a formula for the infinitesimal piece of force. And what we can do is, I could do this later, I could do this now, I'll just do this now. So if we integrate both sides, the integral of the infinitesimal piece of force is the total force, kind of like by definition. So force equals the integral from k q dq over r squared r hat. Now, what you could normally do, and actually I think, I haven't tested it on a harder problem, but I believe that this should work if you were doing a harder problem. Like say this wasn't, you know, the nice in the center of this of the semicircle, and maybe even if you didn't have a uniform charge density, although actually that would create a different issue that I don't think is going to come up in this problem. But so if we didn't have some of the nice symmetry that was given in the initial problem, I believe what you'd have to do is say fx equals this thing all with in the x component direction, and then fx plus this thing in the y direction. You'd have to switch it into vector notation. So we're going to do that, but what we're going to discover is, so let's go back to writing with another color real quick, because I'm going to get rid of this again. So if we take this, and I already did this over here, but I'll just do it again real quick. If we break this down into its x component, that's this, and its y component, that's this. But because of the symmetry here, you'll see that, so this angle is right here. There's another one that would be right here that points out like this, that has the same exact x component, but in the same exact y component, but in the opposite direction. So what's going to happen is we're going to have, I'll just get rid of it. So we're going to have F, the force in the y direction is going to sum up to be equal to 0. The net force in the y direction is going to equal 0. It's all going to cancel out and balance out. So we can completely ignore that part. And we're just going to be adding, as I showed over there, all of the x components associated with the forces. until we get that semicircle shape. So that's what's going on. So we want to consider, we actually don't want to find, we're looking for the full f, but in this case, I'll get rid of these yellow and then write it in this purple color. Okay, so let's write it in purple. So we're going to say that the net force in this case, I'll write net there, which is what we're looking for. This is also net, I just didn't write it there, equals the x component of the net force. Okay. I didn't really have to write net here actually because net, the f by itself without the d in this case does represent the total net force. But anyway, so we're actually finding the x component. So this is equal to fx. All right. So now let's start to substitute some things in. So we have f equals, so right now as I've written it, we've actually solved for f. F equals this right here. But this is not very useful in most cases. And generally when you solve one of these, you want to get it to where, as I said before, you break it down to where it only takes algebra to get a solution, where it's more of what you would think of as a formula, so that you can just plug in numbers, maybe do a little bit of algebra manipulation and get your answer very simply. So that's the end goal. And this has not reached that end goal, but this is technically the formula. This is a formula for the force. All right. So we're going to go the integral, and I'm going to pull out some stuff. Anything that does not change. So what's happening is this dr, we're going to imagine that, so this is our dq. And that's what we're going to want to integrate over, is from this point in the dq, as we add up all of the dq's from here to here, which is adding to infinity because dq is infinitesimally small. And that's the crazy thing about calculus, is you can take something infinitesimally thin or small, add up an infinite amount of them, and the end result is anything you want it to be, but that anything you want it to be is based on the constraints given. So in this case, the constraint is this this horseshoe shape here. All right, so so what we're thinking of is, as we add up the different dq's, we're going to imagine adding them up. You can start anywhere you want it. I'm going to imagine starting here for right now. Maybe I'll change it later, but start right here and go around and add these dq's. So while we're in the process of adding all these dq's, so as we're thinking of sliding this way around the semicircle, what values change and what values don't. If they don't change, we can pull them out of the integral sign because they're considered constants. And the ones that do change are considered variables. Technically, all of these are variables in some sense right now because none of them are actually numbers, but these are the ones that don't change are constant variables, and the ones that do change are variables. So maybe there's better terms for that. I'm not sure. All right, so k does not change. K never changes because k literally is a number. It just stands for a number. It can only be that one number. So q is this q here. Does this charge change as we move around? No, it does not. What's next? dq will like technically the value of dq does not change, but as far as our purposes, yes, the dq does change. So one moment it's this dq, then it's this dq, then it's this dq. So dq has to stay inside. All right, does r change? Well, this is a bit tricky, but that's why I wrote r instead of dr. So here the direction of r changes, but we're actually accounting for the direction right here with this r hat that I forgot to write the hat sign on earlier. This r hat accounts for the direction of r. So this is really the magnitude of r. Does the magnitude change as we move around this? The answer is no, it does not, because it's always the radius of this semicircle. R squared. So now we just have, was that right, dq? Huh, I did it different earlier and there's a lot of different ways to do this problem. I did it earlier, then I got caught up in a snag, but this is somehow ended up so much easier this time. All right, so now r hat. Does r hat change? That's the direction here, and yes, r hat does change. Um, so except that we know for r hat, we actually just want the x component. This is part of where I get, actually this is where I get hung up. So we just want the r hat is going to be in the x direction. So what we're saying is for every dr, we want the x component of dr. So, let's see, where do I want to put my angle? I think I'll put it right here. So if we imagine this being the y-axis and this being the x-axis, this being the y-axis. Okay, and so this angle here is theta. It's going to make the problem work out a little easier if we consider this angle 0 and this angle pi. So if you imagine taking my picture and rotating it this way for the normal math layout, but we can just leave it the way it is and move the start value and the end value. I think I'm gonna have to. I have music playing. I think I have to stop it because it seems to be slowing down my tablet. All right, so yeah, it's a lot better. Okay, so now this here is theta. Due to geometry rules, this is also theta. So what we're actually looking for, the component of the force that we're concerned with, is this component, this piece right here. This piece is equal to, let's say this right, say just cosine, in this case, sine of theta. So we're going to take dq and multiply it by sine of theta. Got my dq floating up in the air there. I thought I was going to have to write something under it, and I did not need to. And that accounts for everything with k, q, dq, r hat. So I happen to write this outside of like what you would think of as outside of this expression, but it could be it's technically inside still. And then the question we have to ask once again is, does theta change as we move around this semicircle? And yes, theta does change. Theta is going to actually go from 0 to pi. So I keep pushing the wrong button. So this is equal to k q over r squared times the integral sine of theta dq, and the thing, oops, not theta, q. So now this is also technically a solution. The trouble is you can't solve this either because you can't take the integral of theta with respect to q because they're different variables. So we have to get either this in terms of theta or this in terms of q. I'm going to get this in terms of theta. So dq is the thickness of this, and I think it's going to be equal to like s times theta, but I actually have to look that part up real quick because that's where I got hung up before. dq equals, like it's theta times s. We don't want s though, we want theta. I think it's theta times r. Let me make sure. No. Q over pi. Why is that? Okay, because our angle goes from 0 to pi. So I see how they did that. There's different ways to do this part too, but I saw somebody do it this way and I liked it this way. Q over something equals TQ over something. So Q relates to pi as TQ relates to d theta. So if we imagine that these are true in both senses, so Q happens to go from the total length of this in radians is pi radians. So Q goes from 0 to pi. So its magnitude, its length is pi. So we have Q over pi. And then if we also imagine going in the same direction, that's going to say that these are the dq's moving this way relate to the d thetas moving this way. And yeah, then of course we have to line up the q's with the dq's because those pair, and pi's with d theta. Since pi is an angle measurement, it pairs up with d theta. So now then we can solve for dq, the thing we want to sub in here. So q over pi equals, q over pi times d theta equals dq. And now q and pi are not going to change as we're moving around this, so we're not going to change those. So force equals, let's bring those to the outside, k q q over pi r squared times the integral of sine of theta d theta. Except, yeah. Yep. And now, so now what we can do is, oops, I wrote q there, d theta. Now we just have to ask ourselves, what's our starting and what's our ending point? You can pick different values as long as it matches up with the picture. So if we imagine this being the angle 0 radians, and we go a full semicircle, then this is the angle pi radians. So we're going from theta equals 0 to theta equals pi. And now we're getting really close to done. So this is equal to k q q over pi r squared times, this is going to be negative cosine of theta from 0 to pi, and then this is going to be equal to k q q over pi r squared times, so what's cosine of pi? So if we draw our unit circle right here, because that's the way I like to do it, and pi is this angle here, which is the point -1, 0. This is cosine. So cosine of pi is -1. We're going to take the negative of that, so we're going to get a +1. Now we plug in 0. This is 0, angle 0. It's at the point 1, 0. Once again, cosine is the x value. So cosine of 0 is 1. So we're going to minus a -1 because this makes a negative sign, and then normally you would put a negative sign because you're subtracting away the second value, so it actually ends up being plus. So +1. And now we're to what's like our final answer. K q q, 2 times kqqq over pi r squared. And I'm going to leave it like this. You could also substitute out the k, and you could put in a lambda for charge density, and you could do some other things. But this is a formula that you can work with. So now let's let me double check my, yeah, that's what I had there. Okay. Let's get rid of some of this stuff. And talk a little bit about what this means. And then I was going to go over several things, but actually maybe I'll make a separate video for everything that I wanted to go over because I see that these are, this is already really long. So this is equal to the force in the x component of the force, which is also equal to the total force because the y component of the force canceled out to be 0. So yeah, so you can now do some things to play with this. So now this is a formula. So the first formula up here, which I'll label number 1, goes with this setup right here. So if you have this setup, just 2-point charges, you would use this formula. If you have this ugly setup looking like a magnet right there actually, but it's not supposed to be a magnet, then you would use this formula. And you can actually use, as I just showed, the original formula in this setup, but you can't use it the way it is. You have to apply calculus to it to be able to use it. But let's say you don't know calculus, or to be honest, it's really easy to make mistakes when you try to apply calculus to these things. So unless you're like absolutely amazing with calculus, it's not a bad idea to have um, some, like I suppose if you were really working with uh, these kinds of things all the time. I don't know that many people would, but if you were, you'd probably want to have already worked out a lot of the different types of secondary formulas like this from first principles and from applying calculus, so that way you don't make it's very easy to make a mistake if you try to derive this every single time. But anyway, so this is like a secondary formula. And as I showed earlier with this one, you can solve for Q1, you can solve for Q2, you can solve for R squared, you can solve for F. Or if you didn't know K, let's say you wanted to verify K, you could somehow use this setup and physically measure the force between the two charges, measure the value in coulombs. So the force should be measured in newtons. Q1 here should be measured in coulombs. Measure Q2 in coulombs, and then measure the distance between them in meters. And then solve this for K, and you could find out what K means. You'd verify that K, so let's see, so K equals, it's going to be F R squared over Q1 Q2. And you're going to find that that equals 8.99 times 10 to the ninth. And the units on this are newtons times meters squared over coulomb squared. So you would be able to verify this, right, from this setup. So there's a K down here. You could also verify K from this setup, but you wouldn't use this formula. You would pull it from here. So you could say, using this setup, you would see that K equals, we're going to have F times pi R squared over top of 2 Q Q. So in this case, we'll still find that K equals 8.99 times 10 to the ninth newtons times meters squared per coulomb squared. But you're going to be just taking different measurements from reality. So you would measure the radius. First of all, you're going to have this be a semicircle, and pretty sure it has to have uniform charge density. Yeah, it'll have to have uniform charge density. All that jazz. This has to be in the center of what would be the entire circle if it were a whole circle. So then, assuming all that's true, you would measure, well, I guess now that I look at this better, I don't think you can really do this way because I don't think there's going to be a way to measure this force. That was the whole problem. That's why calculus was done in the first place. But so, okay, well, I guess you couldn't use this one here because not unless there's some way to measure the net Well, I mean, I guess technically you could because we happen to know that this is also the force in the x direction. So if you measure the force in the x direction that's acting upon this particle, then yes, you could, because we already verified earlier that the force in the x direction on this particle is the total force on this particle. So yeah, you could. So you measure the force on this particle. You take pi, which is just a number. Then you take the radius here and square that and divide it by 2 times the charge value of this charge times the total charge value of this horseshoe-shaped thing. And then that would be a second way you could verify K. Um, Something that's often done with these, let me think for a second to make sure it's going to work in this case. I'm not sure that it's going to. So no, this one wouldn't work here. Yeah, I think that's about all that you can think of that's interesting from this example. And I gotta think if I'm gonna go into another example or not. I think I'll stop there. That way if I make any mistakes on the second one, I don't have to re-record the whole video.